So we all have this sense of what we think algebra is, right? The ways that we encounter algebra coming up through the grades, all sort of funneling us toward calculus, get us to think about algebra as a set of processes and rules and ideas that help us to simplify algebraic expressions and to solve algebraic equations. So as to help us, for example, model relationships and patterns among data sets and observe variables and sketch graphs and do all kinds of different things. There's all these different tasks that go into it, but at its heart, it's kind of about relationships between things, right? Being really vague about it. Relationships and patterns. And so our question today is, how far can we push that? How far outside the envelope can we find algebra? Finding familiar algebra in unfamiliar places is one of the themes, I hope, of this course, right? And so as we wander out into the land of knots and braids and tangles and all this other weird stuff and permutations and anagrams and stuff that we're going to talk about today, we want to ultimately be able to bring that all back to say, oh, here's something familiar. Here's something that looks like algebra from within these wacky structures that we study. So I want to hone in on the word operation that was mentioned as part of this initial discussion. That is kind of where our study begins. And what I think of when I think of an algebraic structure is we really need kind of nouns and we need verbs. We need objects that we can sort of understand, and then also ways to act upon those objects, nouns and verbs. There's a whole branch of mathematics called category theory, which is basically a way to try to abstract as much of mathematics away and think about objects and relationships, which are called sort of, functions in between those objects. So to that end, let's talk about how we might define what an operation actually is in as much generality as that we can stomach. So if I have a set S, and it's going to be a set of elements, these are my nouns, my objects, right? Maybe they're integers because we're in 4th grade or something, so we have positive and negative whole numbers, but we don't have fractions. Maybe it's the rational numbers. Maybe we're in college and we have the real numbers, which really is the right time to entrust people with the secret knowledge of the real numbers is college, because it's a scary place. Or maybe those elements are not numbers at all. Maybe they're shapes, maybe they're colors, maybe they're ideas, right? These objects could be anything in principle. But it's when we affix an operation on top of those objects that now it starts to feel more like algebra. And so an operation on a set is a function that assigns to every collection of n elements of S an output element of S. So maybe I have an operation that takes one element as its input and it spits out one element as an output. If it's just one, then we call that a unary operation. If it takes two elements of my set and spits out a result, then we call it a binary operation. If it takes 3 elements and spits out a result, we might call it a ternary operation. If it takes 12 elements of my set and spits out 1 at the end of the process, we call it a 12-ary operation, right? So really, this is sort of a flexible structure that allows us to think about all kinds of different types of operations that we could define on a set. So just by way of some examples, if I'm thinking about the integers as my set, then I might think of negation as being a unary operation. You give me a 3, I spit back -3. You give me a -15, I spit back 15. You give me 0, I spit back 0, right? That's a unary operation because you're giving me one element and I'm giving you back one element. Binary operation on the set of rational numbers. Whoops, that's a typo. I should say the set of rational numbers. The multiplication operation. You give me 2 rational numbers, I give you back the product of those rational numbers. So if you give me 1/5 and -20, I give you back -4. You give me -2/5 and -5/2, I give you back 1. Right? So that's a binary operation because I'm taking 2 and I'm giving you 1. There aren't many ternary operations that we think of out there, but it's certainly not too difficult to define one, right? Maybe I'm in 3 dimensions and you give me 3 vectors in 3 dimensions and I give you back 1 vector, which is the sum of the 3 that you gave me. I just add all 3 of them together, right? That would be an example of a ternary operation. And so you might imagine how we could define all kinds of different n-ary operations on a set. And so when we say an algebraic structure, the minimum amount of stuff that we need in order to define an algebraic structure is a set of elements, so you have to give me some nouns to work with, together with one or more operations on that set. And even just having one, a single unary operation or a single ternary operation or something, is enough to give me an algebraic structure. And so depending on what those objects are sort of concretely and what kind of operation we define upon them, there can be all kinds of different algebraic structures. And we don't even begin to scratch the surface, even in our undergraduate curriculum, with all the different types of algebraic structures that are out there. We spend most of our time in abstract algebra studying a particular kind of structure called a group, right? But there's a lot of structures besides groups. There are structures with less form than groups. There are structures with more form than groups, like rings and fields and things like that. But all we need to be doing algebra is a set of elements and an operation on those elements, regardless of how many items that operation happens to take. So the first thing that I want you to do is to try and bring this idea back to earth a little bit with your team. And see if you can come up with a brief description of an algebraic structure that students might first encounter in, I don't know, early elementary school. So my kids are 6. I have twin sons that just finished kindergarten. What algebraic operations, well, algebraic structures might they have encountered at this point in their education? What's one that they might not encounter until later on in elementary school? And then maybe what's one that they might not encounter until high school? So see if you can come up with some examples. And in each of these examples, see if you can describe what is the set of elements, what are the nouns, and then what is the operation, and what is its valence? Is it a unary operation, a binary, a ternary, right? So see if you can just come up with some concrete examples to bring this back home. We'll take about 10 minutes in your team to do that. So just to pick a selection of some of your responses on this. I like this really vivid description that team number 1 gives here of a unary operation in the early elementary school classroom, where the operation is something like addition, where you learn how to add by operating on a set of cookies, right? Where if I take a certain number of cookies and then another certain number of cookies and I combine them together into one plate, right? That gives me a binary operation where I start with some number of cookies and some other number of cookies, and the result is I have a different number of cookies, right? So that's one way to kind of look at how addition is conceptualized in the early grades. Another way that the other team sort of came up with here is in thinking about skip counting. So skip counting is definitely something that you start doing in these early grades, where if we're skip counting by 2s, for example, maybe one of the exercises that we do is you give me a number and then I give you the next number skipped up by 2, right? So you give me 20, I give you 22. You give me 12, I give you 14. That would be a unary operation on the set of even numbers. It's also a unary operation on the set of odd numbers as well. But if you're just learning how to skip count, very often you start with the first even number, greater than 0. So yeah, there is a place for a unary operation in the elementary classroom. If you're expanding upon skip counting into multiplication, as this team talks about here, then you're talking about a binary operation on multiplication of integers. You give me 2 integers, I give you their product, right? That would be a binary operation we might learn about in the late elementary classroom. And then in high school, I like this example as well, where we have a set which is the side lengths of a right triangle. So you give me 2 sides of a right triangle, and I supply for you a trigonometric function of one of the angles in that triangle, right? You give me the opposite and the adjacent side, and I give you the tangent of the angle that those two subtend, right? That would be a binary operation, kind of. This one I want to push on just a little bit, because while it's true that we're taking 2 elements from my set as input, the output that I'm getting is not really part of the same set that the inputs came from in this example, right? If you give me 2 side lengths of a triangle and I find the tangent, I find the ratio, the result is a ratio. It's not a length of a right triangle. It's some quantity that's related to the angles. So probably the most important thing about an operation is it has to give you the same type of output as the inputs that you gave it, right? So if you give me real numbers, I need to give you a real number back. If you give me integers, I have to give you an integer back. If you give me 6 matrices, I need to give you a matrix, the same kind of matrix back, right? So that's just one place where in this example, I would just push on that a little bit and say, well, maybe the way to think about this would be you give me 2 lengths of a right triangle, I can give you the length of the third side using the Pythagorean theorem, right? Then my set is the set of all line segments that are a part of a triangle, for example. You give me 2 of them, I give you the third one back, but the thing I give you is of the same type as the 2 things that you gave me. So that's kind of an expression mathematically of what we call closure, right? Whatever we're taking in as input is the same type of thing that we're giving out as output. But that is sort of where algebraic structures come from, right? It's a way of defining an operation through which we take a bunch of elements, 1 or 2 or 3 or more, however many, and we give you back another element of that same type. And it turns out that the operations that we study the most are binary operations. These are probably the ones that you've found it easiest to think about in this previous example. So the next thing we want to do is shift and start focusing, start specializing a little bit on what do we get if we study binary operations on a set of elements.